Well, good day, everyone, and welcome to Authenticate. For those of you watching it on, I guess, West Coast time, this is our lunchtime lunch and learn session. My name is David Turner, and I'm the Director of Standards Development at the FIDO Alliance. And what I'm going to be doing today is giving you a general overview of what FIDO is from the standpoint of the specifications, why we built it, and how it's being used, for some of those who may not be familiar with it yet. The goal of the FIDO Alliance was to address a number of problems, both from a security and usability standpoint. Everyone's familiar with the use of passwords. Not the best in terms of security and certainly usability these days, given the number of accounts we have to member. Bit of a challenge for everybody to make use of them. In order to add security, there's various means for adding second factors of authentication. And frequently they involved other hardware devices that provided one-time passwords or one-time passwords from your phone. And while they improved the security, they often made the interaction a little more clumsy and a little more awkward. And not only that, but the one-time password approach, whether it's through SMS or some other means, is highly prone to both phishing and sometimes man-in-the-middle attacks. So FIDO's goal was to provide an open set of standards for simplifying how users do their authentication and provide higher level of security at the same time. So the idea is that you have a simple gesture combined with the possession-based authentication to provide that simple, easy-to-use experience. So I think it's worth going over some of the threats that, the most common threats that people are facing when they're online to help give a context of where FIDO fits in and where it really adds value to protect the users. If you look at number one at the bottom, that's the most common scenario that we hear about on a daily basis, where passwords sites are hacked, whether it's a healthcare company or a financial institution. Millions of passwords are being stolen and sold on the dark web, and then they're used to attack other services, emails, bank accounts, and so on. So that's probably one of the biggest. Number two is a scenario where information is stolen directly from a device that you may have. It can come from malware and other similar kinds of attacks. And the idea is that the passwords and credentials are stolen right off the device and then reused for logging into other sites and presumably doing malicious things. Number three is a common situation where credentials or information, again, is taken off a user's device. And this time it's used to misrepresent them to other places, possibly using the information to help reset credentials and reset passwords so that they can do an attack. And the remotely attacking of the user device is typically the man-in-the-middle or phishing type attacks, where you're convinced or users are convinced to log on to a site, provide the credentials as you're using it, and then those credentials are then stolen and reused elsewhere. Those first four attacks are generally considered scalable attacks because they can be used to attack 1,000 people or 1,000,000 people with largely the same level of ease from the standpoint of the attacker. And that's the area where the FIDO protocols and authenticators add the most value and have the greatest impact. But because of the way that the authenticators are built in terms of the securing of hardware and such, they can also provide a level of mitigation against some other physical types of attacks, because in many cases the hardware is built in such a way that it's physically difficult to get the information out, even when you have physical access to a device. So I'm going to go through what the authentication with FIDO looks like relative to what you're used to seeing on the web. So this is a traditional picture. A user logs in, authenticates through their device to a server. Often there's some risk analytics going on in the background to figure out, is this person coming from the right location? Are there any oddities about how they're logging in? But one of the problems with this scenario is that the user is providing information to something on the device. It could be an app, it could be a web browser, and that's typically all based in software, things that can be hacked. And so there's a level of uncertainty when a user is providing that information that then gets passed through the internet to the server. And of course, once it's moving through the internet, there's risks of it being captured through man-in-the-middle attacks and so on, and reused or abused. That's what the old authentication looks like when we're using passwords. And in that scenario, again, passwords can be stolen from the server. You might be entering the passwords into an untrusted environment. You've got the big problem of too many passwords to remember, which of course creates all sorts of usability problems because people can't remember them. From the relying party standpoint, they get, users just leaving the website. They go, they fill in their shopping cart, they try to check out, and they have to provide their password. Oh, don't remember what it was, or it's an old one that I used before, and off they go. They don't make the purchase. And then there's the problem of having to put passwords into the phones themselves. Everyone's very familiar with all the kind of typos we make when we're doing texting and such, and doing passwords with often they're very cryptic and hard to remember codes. It can just be a real nuisance. So the overall experience introduces lots of risk and a number of usability challenges. So the first difference that we have with modern authentication, what I'll call with FIDO, is that you're no longer verifying yourself with or doing the verification with just some unknown device. You now have a situation where we separate what's going on between the user and what we call the Authenticator, which now acts like a proxy to the authentication process. And then the Authenticator talks between the Authenticator then talks to the server. So we no longer have this problem of a password being passed all the way through from the user to the server, and therefore it's something that can't be stolen all the way. So we've split the things into two parts. And what happens here is that the user starts off by now, instead of entering a password, they authenticate themselves with the Authenticator. So it's a matter of the user proving themselves, either presence or uniquely that it's them, to the Authenticator. And then the Authenticator, using public and private keys, does the authentication based on a challenge response protocol with the FIDO server. So again, we've partitioned we partitioned the parts of the user authenticating itself to the Authenticator and the Authenticator with the FIDO server. And because we're using public-private keys instead of shared secrets, which is what a password is, we no longer have the problem of passwords being stored on the server and creating risk for the end user. So looking at this from the same standpoint as the old model, first, what we have now is there are no secrets stored on the server. So the hacking opportunities there are significantly reduced. The Authenticator can't be tricked by phishing. And one of the main reasons for that is that when you set up the Authenticator, it's bound to the user and to the site that you're connecting to. And during the flow, which I'll show a little bit later, part of the authentication process is it compares the ID of the relying party that wants to authenticate with the ID of the relying party that created the credential in the first place. And if they don't match, then there will be no authentication. The authentication will fail. So this aspect of FIDO protects the user against both phishing and most man-in-the-middle attacks. So it provides a much more robust and trustworthy way of interacting, both through applications as well as through web apps. There's nothing to remember as you go from site to site. So it makes it a whole lot easier for users to do their logins, even while knowing it's much more secure. And in general, it's a single gesture. And that could be just touching an authenticator to prove that there's actually a person there. It could be it could be touching for a fingerprint. It might even involve using a PIN if you're looking for a higher level of user verification as a part of the process. I just want to touch quickly on generally what an authenticator looks like, but also where biometrics come into play. In this diagram that you see, the trusted execution environment represents the container for the place where all the FIDO transactions take place. And within there, you generally have a comparison element where it says user verification or present, which is integrated again into the same hardware. And the benefit of this is that if, say, you're using a fingerprint reader, the fingerprint reader does the enrollment and saves the template on the protected device. The information for doing biometrics never goes to the server, so there's no risk of it being stolen off the server in the same way passwords aren't. And when you do the verification, again, that's all done locally in a protected space. So the user has high degree of confidence that unless somebody has physically, and I do mean physically, like cutting open the plastic and so on, gotten into the hardware, then they can trust that it's doing the right thing. One part that's common, I'll point out here on the right, and I'll talk a bit more about this in a bit. When an unlock has happened, you'll notice that there's something called an attestation key and then the authentication keys. And I'll cover those in a little more detail shortly. So the authenticators, and this is one of the other benefits of how FIDO has been built, is that there's a lot of variety available to address multiple use cases. So first we'll see what we call the platform authenticators. And these are the ones that are built right into the hardware. So it's what's used by Windows Hello for logging in. It's integrated within Android, and we should be seeing something very similar coming from Apple in the very near future. And then we have another scenario, which are called roaming authenticators. And these can be USB dongles, they can be based on NFC or Bluetooth, or they can actually be embedded into another device like a cell phone. And the advantage of the roaming authenticator is that you can actually use that authenticator across multiple devices. So for example, if I have a USB authenticator, I can use it on my laptop to log into mybank.com just using the authenticator. And then I can go to my cell phone and use the NFC aspect of that same authenticator to log into mybank.com again without having to enter the password. So by having this roaming authenticator, it gives you the freedom to use the same key across multiple devices. And each scenario has its own benefits depending on what levels of security and what works best for your particular scenario, both in corporate environments as well as consumer use. And then at the interaction level, again, there's a large variety of ways in which you can interact. In some cases, all you need to prove is user presence. So let's say you've got a USB dongle sitting in the USB port. If somebody tried to attack your machine via software, they wouldn't be able to trick the key into giving up the information, because the key requires that a user, a literally warm body, touches the key and proves that there is in fact someone there outside of the hardware, let's say, that is using it. And then there's also the notion of user verification methods. So the first was presence, just somebody's there. The next is user verification. And in those cases, you can use pins, you can have visual face recognition, voice, fingerprint, what have you. So again, there's a lot of variety that you can use for the different types of scenarios that you may have in your environment. And the last thing I want to talk about here to fill in things is to emphasize other aspects of the whole FIDO ecosystem to help provide richness and robustness to the system as a whole. I mentioned on a previous slide the notion of an attestation certificate or an attestation object. And this is a piece of information that the authenticator can provide to the relying party when an authenticator is being registered for use. And the idea is that this is a way of proving to the relying party that the authenticator being used is what they say they are. Every authenticator has or batches of authenticators, batches tend to be 100,000 or more, have a unique number called an AAGUID, and associated with that would be the attestation object. Using the metadata service that FIDO provides, a relying party can go get the certificate for that attestation object, do a comparison, and then be sure that it is a legitimate authenticator that they're interacting with before completing the registration project or process. And so this allows for more trust in the system to help mitigate against situations where people try to create phony or counterfeit authenticators. So what that leads us to is a much better, a much stronger authentication system. It uses public private key and cryptography instead of just using simple shared passwords. The keys always stay on the device. I forgot to mention that earlier. In that picture I showed previously, that when I was talking about the biometrics, I highlighted the the attestation certificate, but also the authentication keys. Those are all maintained on the device, by the device, so that it's never shared anywhere and can't then be stolen. There are no server-side secrets. There are no third parties in the protocol to worry about, creating gaps or new attack vectors. If you're using biometrics, the templates that are there never leave the device. And can't remember now if I mentioned, yes, I did. I talked about phishing and man-in-the-middle protection. I talked about how when you do the registration, part of the registration is recording in the credential the relying party that is used, that the credentials are being created for. But every time you create a new credential with a new relying party, that creates a new unique key, such that there is no way to know that the private key or the public key from one registration belongs to the same entity that registered it at another location. And as we talked about earlier, the whole idea is to make all of this work more easily for the end user as well. We're getting rid of the need for our ongoing use of complex passwords. It tends to be a simple gesture or simple interaction to log on. It works in the flow of pretty much all existing authentication services. You can use the same authentication mechanism on multiple devices, or the same one for multiple services. And in general, it just makes the whole flow and the whole process a faster, more convenient, and typically a more seamless process for the users. So I'm going to touch briefly now on the flows themselves. Don't need to spend a huge amount of time on it, but at least want you to see what the actual flows look like. So when a user, or when a relying party wants a user to, or lets a user register a new authenticator with the site, the relying party provides information about itself that it delivers to the code that's managing the authenticator, and it includes things like the origin of the site, which is the thing that's used to make sure that when authentication is done later, that it's the same origin asking for the authentication as created it. And there's a variety of other parameters that are provided as well. This information is then given to the authenticator, which then produces a unique pair of public-private keys. And again, this is unique to this combination of this authenticator, this relying party, and user. So that if you did it again with another server, again, this pair would not be the same and therefore unlinkable. So all of this information is then gathered up, a signature is produced, and that information is ultimately then passed back to the relying party. And you'll notice here, it talks about the attestation certificate as well, which, as I mentioned earlier, is the means for the relying party to determine that this is in fact a genuine authenticator. And then of course, the relying party will manage, in whatever way it does, the keys so that it can use them in the future for doing registration. Now, when it comes to registration, it's a very similar flow. The relying party issues a challenge along with any other options that it may be using. There are a few different options you can set when you're both doing the registration and during authentication. That information again is hashed, and along with the relying party ID. And at this point, the authenticator does the appropriate lookup, finds the key, and then creates a signature again, including the challenge, pardon me, which it then passes back to the relying party, who does their own lookup to make sure that the keys match the key that it has and ensure that it's valid. You'll notice that over here, there's the counter, which means that it increments a counter, and that counter is then passed through as well. That's another check mechanism to make sure that something funky isn't going on with the authenticator. The idea is that if there is a wild difference in the numbering, especially if the counter is suddenly less than the last time the relying party checked, that's going to indicate that there's probably something wrong with the authenticator, and therefore it's another parameter it can use to fail the authentication if it thinks that's the right thing to do. So now, how do these things look? I'll say in the code itself. How do these fit into the sites that you're building? So again, here's a sort of a typical view of how a system may be set up. You've got your, a relying party server. There's a relying party bit of code and the FIDO client running on the client. And you'll notice that we've included bound authenticators, or what I called earlier, platform authenticator, as well as external authenticators. Now, first, when I talk about a relying party client or relying party app, that can either be a native application running on a laptop, on a phone, or, as is often the case, that's going to be an application running within a browser. These days, any kind of login type scenario makes heavy use of JavaScript. So what I'm going to show you now is where are the different pieces of FIDO that fit in to help build these solutions. So within the W3C, a specification was built, I'll give you a bit more detail in a moment, called WebAuthn or Web Authentication. And this is a specification that was based on work contributed by the FIDO Alliance because the W3C was determined the best place to do this work because it is a web API for doing credential management. And so we needed it to be built into the browsers in a safe and reliable way. At the platform level, you have another specification called CTAP2, and that spec was developed specifically by the FIDO Alliance. And its role is to actually define the interfaces from a platform, Windows, Apple, Android, and how they can talk to the external or roaming authenticators that I talked about earlier. They can connect through USB, through NFC, or through Bluetooth LE. And so this defines how that communication takes place, and is generally, this interface is generally used by either people who are building a local application or a native application and want to write directly to an authenticator, but more often than not, this is an interface that is built in and then exposed through standard APIs of the platforms. So it'll be available, it is available today on Windows, through Windows Hello, it's available on Android, and looking forward to the same thing being available on iOS and macOS in, we hope, the near future. So Web Authentication, or WebAuthn as it's called, is a JavaScript API that is built into the browsers. And so what this provides is a variety of benefits. One, it's a common API. So you don't have to be writing different code for authentication to accommodate the different browsers. The APIs are the same, and all things being equal, we know it's not a perfect world, but all things being equal, then you can use the same code across the different browsers. And as of today, WebAuthn is supported in all of the major browsers: Chrome, Firefox, Safari, and Microsoft Edge. I should note that you will see the date says January 2019. That's when this level 1 version of the specification was produced. The working group is actively working on the level 2 specification, and sometime in the next number of months, a new version of the specification will be coming out, which is largely an incremental extension of what was already there. Some great new features. I don't mean to suggest incremental means not a lot, but it's a follow-on as opposed to, let's say, a replacement. So just giving you an idea of what, in general, the JavaScript setup might look like for this. You'll see that we create you create a structure here which contains information about the user that the relying party wants to create the create the credential for authentication. And then there's just a simple call to create the credential based on the information. And the result of this is that it provides back the public key and the attestation information to the relying party to prepare it for use in authentication. And again, one of the aspects of how FIDO works is that that process of creating the new credential doesn't happen unless, in this case, John performs an action. And again, it could just be touching an authenticator button to indicate there's a person there. It may require some higher level of verification, like, say, a fingerprint. But the idea is that this creation process cannot happen unless, in this case, John takes an explicit action to confirm that, yes, he approves the creation of this credential. Then once the credential has been created, when John wants to log in the future, again, information is passed, which includes various things, including a challenge. And the request now is to get the assertion associated with John. And again, it requires John's acknowledgement of this request. And again, it could just be a touch on the authenticator. It could be entering a PIN. It might be a fingerprint. But as before, this process doesn't happen unless there's an explicit action taken by the user. Won't go into a lot of details, but in the CTAP interface, you generally have the same two functions. There are other, there's other, typical configuration and so on features, but in general, with CTAP, you have the same notion of making a credential and getting the assertion when trying to talk to the external authenticators. So in all that, tried to show how FIDO provides a more secure way of doing authentication, how it makes it easier and more trustworthy to do authentication, and how all those pieces work and fit together so that more and more people can go out and build more robust authentication solutions using the FIDO specifications. At this point, I want to thank everyone for listening, and I'd like to open it up for questions. Thank you.